If you're a first-time programmer, then you can probably skip this video. But I encourage you to keep going and see what you can pick up from it anyway. Because in this video, I will show how recursion and higher order functions can replace for loops. We'll see how to recover an efficient implementation of the infamous factorial example through the techniques I show here. And in doing so, we'll use everything we've learned so far about syntax, types, functions, and recursion. So let's say we want to calculate choose from directly using the formula n factorial over n minus k factorial divided by k factorial. For that, we need to have factorial. Imagine for a second we were in a non-functional language with for loops and variables that can change their value. The code for factorial would look like this. Int factorial of int n, int result equals 1, for int I equals 2, I is less than n, I is equal to I plus 1. You say result is equal to result times I, and then you return the result. We have a bunch of things going on here, so we can break it down. We have an argument n, which tells us we want n factorial. We have a result to store the result in. Then we have a for loop, where we basically just calculate 1 times 2 all the way up to n, using the inductive or building up or going from small to big approach. After the for loop, we return the result. However, the for loop itself has a few components. The initialization, this sets up I, so that we can count how many times to loop against n. The keep going condition, if this is true, we execute the body, otherwise we exit the loop. And the next step, I is equal to I plus 1. We do this at the end of the loop, and it means we're always getting closer to n. But we can also flip the script and look at this loop recursively. How? The initialization is like the first time you call the function. Instead of an argument to a function, it's modifying the state with a variable. The keep going condition is the negation of a base case check. If it's false, we stop. Since we're going up, we have to check that I is less than or equal to n every single time. This is like our check that k is equal to 0 or k is equal to n in our choose from example. It's a little bit clearer if you write it as a while loop instead. We take the for loop from before, for int I equals 2, I is less than or equal to n, I is equal to I plus 1, result is equal to result times I. We move the initialization out, so int I is equal to 2, while I is less than n, result is equal to result times I is equal to I plus 1. And then we rewrite the while loop as an if statement with an infinite loop. So we have int I equals to 2, loop. If it's not the case that I is less than or equal to n, then we exit the loop. Otherwise, we do result is equal to result times I, and we do I is equal to I plus 1. Especially the last version looks like our function with if base case, then something else keep going. Except instead of explicitly calling the function again with a smaller problem, we're just looping. And this time, the thing that is getting smaller is the difference n minus I. This is what ensures the termination, and in a system of reasoning called Hoare logic, named after Tony Hoare, inventor of the quicksort algorithm, is called the loop variant. So what's the analog of an inductive step for recursion? What do we assume so that we can make the next bit work? Well, here it's that at the end of the loop, after we increment I, but before we test whether I is less than or equal to n, that we have result is equal to I minus 1 factorial. So when I is less than or equal to n is false, so in this case when I is equal to n plus 1, we have result is equal to n plus 1 minus 1 factorial is equal to n factorial as we want. In Hoare logic, this is called the loop invariant. It's what remains true each time we execute the loop body. Now that we've dissected a for loop factorial to death, let's take a step back and think about what we've learned. We've learned that a for loop has all the same elements as recursion, just in a different place under a different name. But now let's think about the features that all for loops share to see if we can write our own little functional version of a for loop in Reason. we could have just as easily written our factorial function like this. Int factorial of int n is int result is equal to n, for n is equal to n minus 1, n is greater than 1, n is equal to n minus 1, result is equal to result times n, return result. This one goes backwards instead of forwards, but it still has the same elements as before. Initialization, a keep going condition of n is greater than 1, or base case of n is less than or equal to 1, with a loop variant n getting smaller, and an inductive step or loop invariant that result times n minus factorial is the answer we want. So when n is equal to 1 and the loop breaks, we have the right answer. Pause the video for a few minutes, try running the code in an imperative language, or even better, working it out on pen and paper, whether what I just said is true. If you're doing this on paper, a good technique is to make a table with the columns as all the variables and the rows as the line numbers, and each cell is the value of the variable after you finish executing that line. Here's an example for n equals 3 to help you get started. So let's think about our function for loop. We know it has type something arrow something because it's a function. We need an initial state, but we don't know what that state looks like in general. It could be anything. In the counting down version of the factorial function, we only have two variables, n and result, but in the counting up version, we have three, n, I, and result. Some of the variables are local to the for loop, like I, but some, like n and result, are from outside of the loop. Instead of worrying about the details, we can just say it's a type, state in general, and leaving it up to the caller to decide what needs to be included. The apostrophe at the start of state means it's any state as opposed to one specific kind. We also know, unlike expressions, such as if b, then e1, else e2 in reason, that a for loop doesn't return a value. It just changes some state, the value of either I or n, and the value of result. Since we can't change things in reason, we can just return a new state and leave it up to the caller to get an answer out. So we can say for loop has type state goes to state. Is this enough? Let's try writing out what we have so far. I'm going to keep the types in for the sake of the video, but you can omit them and everything will work out just the same. The types will help us to keep stock of what options we have when we need to figure out what to do next. Let for loop of state in of type state with the result of type state goes to if fail with base case, then fail with state, else fail with some recursion. Also, fail with is a function of type string goes to anything. It's useful when you're constructing a program bit by bit in a functional language, because you don't have to figure out the whole problem at once. What we have so far isn't bad, but we're missing a few pieces. We know that for an if expression, the base case has type bool, but all we have so far is a state in of type state. We need to figure out how we know when we're done, when the state is in the base case. We need something to convert a state into a boolean, something of type state to bool. We then remember that we forgot to give the for loop our keep going condition. And what does that do? It looks at the state, and then evaluates to true if we should keep going, and false if we should stop. It's a function of type state to bool. So let's change the input type for loop and add it in. So we have let for loop takes a state in of type state and a keep going of type state to bool, returning a state with the body from before. To fill in base case, we need something of type bool. What we have is state in of type state and keep going of type state to bool. By the function application rule for types, we get a bool, so all we need to do is apply them. So we have keep going of state in, and it type checks, so we're done. But not quite. Remember from the for loop example, we're wanting to check the base case, and by our own definition, the keep going condition evaluates to true if we should keep going and false if we should stop. So we can either swap the if expressions, or, like the looping example from before, put a not of type bool to bool around keep going of state in. We can also just change our definition and decide that it's up to the caller to flip the expressions, but for now we want to keep things as similar to a normal for loop for the caller, and also in line with our previous examples where we deal with the base case first. So we write let for loop of state in of type state, keep going of type state to bool, all has a type of state, goes to if not of keep going of state in, then we fail with some state, otherwise we fail with some recursion. Now we want to fill in fail with state with something of the right type. We know for loop has type state, comma state to bool goes to state, and so the thing on the right of the arrow, the whole if expression, has type state. That means we know that both fail with state and fail with some recursion must also have type state from our rules before. Taking stock, all we really have is state in and keep going, and of those, only state in has the right type, so we don't really have other meaningful choices, and so we put that in. If you consider that we just skip over the for loop and do nothing if the keep going condition is false, this is exactly what we want. Now we consider the inductive step. Usually the way it works is you guess at one, it doesn't quite work out, you figure out what you need to fix, and then you repeat until you're done. Now we could replace fail with some recursion with for loop of state in and keep going, but remember, induction is about solving the problem for a smaller case and then using that to make a bigger one. One of the guarantees of functional programming is that it only depends on its arguments and doesn't implicitly use the state of the outside world. So if we pass in the same arguments to the same function, we're going to do the same thing, and here it means we just loop. So if keep going of state in is equal to true, then we'd go to the second branch of the if statement and end up looping to right back where we started. Instead, we need to figure out what we're deciding gets smaller. In the previous examples, it was the difference n minus I, or just the n on its own. Here, we have two things that we can try and change. Either the state in or the keep going. While you could change a function, which we will be doing when we write an interpreter for our own programming language in Reason, in the previous examples, what was really changing was the state, the values of the variable inside it. So the third piece of the puzzle we've yet to use is the body of the for loop, including the increment or decrement to whatever counter keeps track of the loop variant. We need a way to get from our current state, state in of type state, to a new state, or in other words, a function. Let's call it loop body of type state goes to state. It's up to the caller to ensure that the function loop body preserves the loop invariant and also make the loop variant smaller between state in and loop body of state in. So then we have let for loop of state in of type state, keep going of type state to bool, and loop body of type state to state, all returns a state, goes to if not of keep going of state in, then we have state in, otherwise let next state equals to loop body of state in, and then we for loop again with for loop of next state, keep going, and loop body. We can tidy this up in a few steps. First, instead of declaring a value next state, we can just inline its value into the argument. Then we notice that keep going and loop body don't change throughout the for loop, so we can nest a function on the inside that does the looping, whose argument is the only thing that ever changes, state in. Lastly, we can remove the type annotations. We combine all this to get let for loop of state in, keep going, and loop body is equal to let do loop of state in is equal to if not of keep going of state in, then we get state in, else we have do loop of loop body of state in do loop of state in. We also see, by writing it this way, a thing that's called shadowing. Basically, it means that a name refers to its closest enclosing binder. A binder is the name we choose to give an argument. So in the case of the if expression, the closest one is the argument to do loop, but for the expression at the end, it is the argument to for loop. If it confuses you, you can just name them different things, and things will work just the same. Name shadowing is useful because it can ensure we don't capture things or names that we don't intend to from outside the scope we're dealing with. We can actually just get rid of all the names and use numbers, or even arrows, but that's the subject of a very different video. With all of this said and done, we can write our factorial function as follows. First, we declare a type state with I of type int, n of type int, and result of type int. Then we declare the factorial function as an initial state with I equals 2, n, and result equals 1. A keep going function which checks that state.i is less than state.n. A next state function which updates the state with I is equal to I plus 1 and result is equal to result times I. And finally, we run the for loop using these three values and extract the dot result value. We can write this even more concisely using tuples and anonymous functions. And if we expand all the for loop abstractions and then start reducing and simplifying expressions, we can get this final, very concise version of the factorial function, which is let factorial of n is equal to let rec loop of n comma r is equal to, if n is less than or equal to 0, then r, else loop of n minus 1 and r times n, all starting with loop of n and 1. So we've covered a neat little trick that functional programmers use all the time, which is called an accumulating argument. So instead of let factorial of n is equal to, if n is less than 0, then 1, else n times factorial of n minus 1, which expands out into n times n minus 1 times n minus 2, all the way down to 1, before it's reduced step by step to n factorial, we do it along the way, one step at a time. So the real lesson here is abstraction and simplification. We reduced a for loop to 4 elements: the state, the keep going condition, the loop body, and recursion. Then we simplified the function to recover an efficient version. We learned how to deal with different representations of equivalent programs. We looked at tail recursion and efficiency. We introduced the notorious factorial function. And what we did was look at data and transformations, both in and of the code itself. Some things to try for yourself are adding the extraction function, so in this case something like dot result or second, but in generality, to the loop itself, and try writing a sum or even the Fibonacci numbers using this for loop.